Generation of FM, how we are able to generate the frequency modulated signals. So for that, we have two popular methods we call as direct and indirect methods. And you know that frequency means reactance is required. So for that purpose, whether we have like capacitor or inductor, so then only we'll able to generate such type of the signal. So that is happening in case of direct method, and most popular is the indirect method, that is also called as the Armstrong method. There you see that how we'll generate without using any reactance. So still you didn't subscribe our channel, please subscribe it and share with your friends. So already earlier lecture we have seen what is the modulated wave of S of, that is FM. S of t is AC, and we have cos theta I of t, and for the theta I of t we have different values for the instantaneous frequency in terms of when we are talking about frequency modulation. So that written as AC cos, we have 2 pi fct plus you have 2 pi kf integration of m of tau d tau. Okay, this is over 0 to t. So this is the expression that we got as the modulated wave. So here we'll see that how we are able to generate such type of the signal. So either we are going to use the capacitance or the inductance, since if you see that Xc is the reactance of the capacitors, that is the 1 by j omega c, and omega is 2 pi f. So we are able to generate the frequency. Again, XL is j omega L. Again, omega is 2 pi f. So inductance and capacitance is required for the frequency modulation. So this can be done with the help of local oscillators, like we have Hartley, Colpit oscillators. This all can be used. So here voltage variable reactance is connected to the tank circuit. So tank circuit means it is the combination of inductor, capacitors, resistance, that is called as the tank circuits. For that, whether we can use the BJT or FET or Varactor diode to change the reactance. But without reactance, one we are going to obtain, that is called as the indirect method. That is the mostly popular, that is known as the Armstrong method. Okay. So first we see how we are able to generate by the help of direct methods. So here three different discussion we are going to see. One is the basic reactance modulator by using FET. Another we have transistor reactance modulator. Then we have Varactor diode modulators. Okay, and Armstrong method we'll see later. Both are important. So here if you see that in case of direct method, this voltage variable reactance is connected across the tank circuits. So this is the example of the FET, and you know that FET having three terminals, gate, drain, source. So V is the voltage between gate and ground, and here we have capacitor, resistance. This I is the drain current, and here voltage between drain and source is the V. So we'll calculate voltage, current, and later we are going to substitute the value with the help of okay, that will discussion here. So this is the basic reactance modulators. Okay, and apart from this we have like we have by using the Varactor diode, all these things are there. But most important is what here, indirect methods. So in the case of indirect method, what we have here, that is the what was the disadvantage of the direct modulators that we are able to overcome here in case of Armstrong methods. So it is a LC oscillator here, okay, so which cannot be stable enough for communication for the broadcasting purpose. That is another problem. Then we required the stabilization of the reactance modulators. So this was the problem with direct method that we'll see again, okay. So we are coming to the indirect method, which is mostly popular, and it is also called as the Armstrong methods. This is very important question. Many times they're asking, generate, discuss or explain about generation of FM with the help of Armstrong method or indirect method. So here reactance we are not going to use. So already we have seen how to generate the FM with the help of phase modulators. So that message signal or baseband signal is being modulated here. Before that, to pass through the phase modulation, it is going to pass through the integrators. And here operating frequency is 1 megahertz. Okay. So to obtain this wideband FM, we require the frequency multiplier. So that also will have separate discussion. First, we'll see how we are going to obtain the narrowband FM. Then we'll see how to find the wideband FM. Narrowband FM means beta is less than 1. Okay. Wideband FM means beta is more than 1. Okay. And beta is what here? That is the del F by FM. Okay, del F is the frequency deviation, FM is the frequency of the message signal. So here you see this block diagram which is used to generate the first narrowband FM. Here we'll get the narrowband FM, and later here we have wideband FM with the help of frequency multiplier. So this baseband signal or message signal is given to integrators. So that integrated output is given to narrowband phase modulators. So in narrowband phase modulator, another input is what? Crystal control oscillators. And this output of the narrowband FM is given to the frequency multiplier. That is going to give us the wideband FM. So already you are aware of the narrowband phase modulators, but still we are going to see here in the exam, if they're asking, you need to draw this narrowband phase modulator also, as well as frequency multiplier. So in the previous lecture, we have discussion when we are talking about FM. There also we have seen that integrated output is given to the product modulators. And here we have carrier signal. This carrier signal is given directly to the summer here. And the same carrier signal with minus 90 degree phase shifter is being given to the product modulator, that is AC sine 2 pi CT. So here it is coming with minus and here plus sign, that is going to generate the narrowband FM. After that, we have concept of the frequency multiplier. Okay. So with the help of frequency multiplier, we'll be able to obtain this wideband FM. So to when the generation of narrowband FM, so here we have well-controlled oscillators that can help us to minimize the distortion as well as phase deviation by keeping that beta as a small. So beta will be less than 1. So it's going to generate the narrowband FM. Now we are going to take the frequency multiplier so that we'll get the wideband FM. So what is the frequency multiplier? It consists of nonlinear device followed by the band pass filters. And nonlinear device is the memoryless. So here this modulated wave, that is narrowband FM, having frequency of fc and modulation index is the beta, is given to the memoryless nonlinear device. That output is what here? V of t. After that is given to the band pass filters that having mid-band n times of the fc. Then we are able to get the finally modulated wave that having frequency nfc, and this beta become the n times of the beta. So that's why we are going to get the higher value of beta, that is the known as the wideband FM. So here, for example, the output of the nonlinear device is taken as the V of t, A1 S of t plus A2 S square of t plus so on plus n S to the power n of t. So where A1, A2, all n are the coefficients that will be going to be determined by the help of operating point of the device. And it is the nth power load device, okay, from where we are able to obtain. And the modulated wave which is given to the input here, that is the narrowband FM. Already we have seen this is the AC cos 2 pi CT plus 2 pi kf integration of m of tau d tau over 0 to t. So this all equation you need to remember. Many times numerical they are going to ask. So this equation you need to compare to the given equation. So here instantaneous value is what here? fc plus kf into m of t. Same as the previous discussion. So that this mid-band frequency of this band pass filter is what here? N times of the carrier frequency, and bandwidth is also going to be here n times of the transmission bandwidth. One is the bandwidth, another is the transmission bandwidth, that we have separate lecture before this. Okay. So finally, this S dash of t is going to become here, that is the n times fc here. Again, if you see that it is multiplied by n here to obtain this bandwidth, transmission bandwidth n times. So finally, for equation 4, what is the instantaneous frequency? That is n times of fc plus n kf into m of t. So this equation 3 and equation 5 you can compare. So equation 5 here, right side is multiplied by the n to obtain this wideband FM. So these are the part how we are going to see that how this FM is going to work by the help of Armstrong methods. Okay, and later we'll have discussion about how to, even by the help of direct methods. There you can see that by the help of Varactor diode, by the help of BJT, how we are able to obtain the modulated wave. That all we can see there. Now we have discussion about the direct method. So indirect already we have seen, and this diagram is for the basic reactance modulator by using the FET. Okay. So now we have calculation for this. So it can be inductive or it can be capacitive. So how we are going to change? So this reactance depends upon the, or it is directly proportional to the transconductance of the device. So that again going to depends upon the gate biasing, how gate biasing is done. Okay. So here impedance should be the pure reactance. So that means here can be capacitive, inductive, but here we are taking the example of the capacitive one. Now what is the requirement for this? So this base current IB should be much smaller than I, that is the drain current. Again, drain to gate impedance must be greater than the gate to source impedance. So ZGD should be greater than the ZGS. So that ratio, if you see that, it is the 5:1. So now by the diagram, if you see the calculation here, so VG is what here? IB into R. Now we are going to substitute the value of IB here, that is the V upon R minus JXC. So that you can see in this diagram. Okay, IB is here, R, and this C is there. So that reactance is what here? XC. So finally we have equation 1. Then we have to obtain the drain current, that is the GM into VG. So now this value we are going to substitute. Okay, from equation 1 we have VG value that we are going to substitute in the equation 2. So in place of VG here, this V into R upon R minus JX is substituted. So finally, already you know the definition of the impedance is V upon I. So now we have V and I both values. So V upon I from the equation 3. So finally, V get cancelled. We have R minus JXC upon GM into R. So here 1 by GM is taken as the common. So we'll have 1 minus, okay, that is the JX by JXC by R. So X is the reactance of the capacitor. In case if X is much greater than R, then what will happen here? So this value is going to be much higher in compared to 1. So this 1 is ignored here. So this equation 4 written as minus JXC by GM into R. So this is the capacitive reactance. So it can be given as, already you know about this, okay? X equivalent is the XC by GM into R. So GM into R, okay? So X is what here? 1 by omega C. So in place of XC, we have 1 by omega C. Omega is what? 2 pi F. Okay. So finally, we have 1 by 2 pi F C equivalent. This is how we are able to arrange this value. Okay. So here, if you see that C equivalent is what? GM into R into C. So this input impedance, that is the of the device between A and A dash, is the pure reactance. So that is the C equivalent is here GM into RC. So this equation 7, from this what you see that this C equivalent depend upon what are things? Transconductance, that is the GM. Okay. And this can be changed by the changing the bias voltage. So bias voltage is going to control the transconductance, and finally C equivalent value is going to change. And here this capacitance can be adjusted within the range by changing the value of R and C. So this RC is also important here. And GM into RC has same dimension as the capacitor. Since R is in the ohm, GM in the Siemens. So finally, if you see that, it has same unit here. And XC, that reactance of the capacitors, should be much greater than R. If it is not happening, okay, reactance of the capacitor is not greater than R, then gate voltage will not be 90° out of phase with the applied voltage. So impedance no longer will be the pure reactance. So these are the problem here in case of direct method. So generally we are going to consider here Xc equal to N times of R, and Xc already is what, 1 by omega C, so that is going to be equal to NR. So from here if you find the capacitance value, C is 1 by omega NR and omega is 2 pi F, so we are getting the equation 9. Now this substitute the value of equation 9 into the equation 7. So there we have C, okay, Gm into R into C. So C value is substituted from the equation 9. So finally we have 1 by 2 pi Fn R. So this R get cancelled. So we have Gm by 2 pi Fn. This is the equation number 10, C equivalent new expression. Now some numerical also we can see, sometimes they used to ask, okay, here what they're asking, determine the value of the capacity reactance obtained from a reactance FET whose GM is 12 millisiemens. Assume that gate to source resistance is 1/9 of this reactance of the gate to drain capacitor. That frequency is 5 megahertz. So what is given here? Transconductance is given 12 Siemens. That is 1 by 1/9. So N is what here 9 and F is given 5 megahertz. So already we have expression for C equivalent Gm by 2 pi Fn. So from here, if you make the rearrangement, okay, just cross multiplications and rearrangement. So we are getting the value N by Gm, that is equal to 1 by omega C equivalent. So this omega by C equivalent is what? Reactance of the capacitor. So now N value is 9 and Gm value is what? 12 into 10 power minus 3. So finally it is the reactance of the capacitor is what here? 750 ohm. Another question is about mutual conductance of a FET varies linearly with the gate voltage. Between the limits is given what here? 0 to 9. Okay. So this is the 0 to 9 millisiemens. The FET is used as a capacitive reactance modulator with, that is the XCGD. So that is the capacitance reactance between the gate and drain equal to 8 times of the resistance between gate and source, and is placed across the oscillator, that circuit, which is tuned to the frequency of 50 megahertz by a 50 picofarad fixed capacitor. What will be the total frequency variation when the transconductance of the FET is varied from the 0 to the maximum by modulating voltage? So Gm is given 0 to 9 millisiemens, N is given 8 here. Okay, it is 8 times. So it is the 8. Frequency is given 50 megahertz. Capacitor is given what here? 50 picofarad. So one by one we are trying to find the values. So here we are considering Cn is the maximum C equivalent of the reactance. So that is going to be 0 here. Okay. Then we are finding Cx, that is the maximum C equivalent. So that is the Gm by, since why it is 0 means Gm value is ranging from the 0 to 9 milliseconds. In this first one we substitute the 0. So this entire value of Cx is going to become 0. So the maximum Gm we are taking as the 9 milliseconds. So milli means 10 to the power minus 3, 2 pi, and F value is substituted, N is 8. So finally we are getting 3.58 picofarad. Now we are trying to find Fx by Fn. So that is the, the frequency by oscillation frequency. We have F equal to 1 by 2 pi root under LC. And in the second case, when you are going to use that, we have C plus Cx inside. So after rearrangement, we are going to get root under C plus Cx by C. And Cx already we got here from the 3.58 picofarad. So that value is substituted. And capacitance is given 50 picofarads. So finally we have 1.0352 is the ratio of Fx by Fn. So now another formula we have, Fx by Fn is the F plus del by F minus del. So from here we can find the value of del. Just rearrangement we have to do, and this value we have to substitute, and F is already given. Okay, so on the basis of that, if you see that here we have del equal to how much? 0.865 megahertz. And so frequency deviation 2 times of this del, so that we have 1.73 megahertz. So like this, how numerical they are going to ask. Now different types of the reactance modulators. Here we see that different parameters, when it is capacitive, when it is inductive. So RC is capacitive. If G, this is the impedance between gate and drain, between gate and source, and condition is here. So here we have C is connected between gate and drain, and here G gate and source we have R, and condition is X is much greater than R, then C equivalent value is GM into RC. So that derivation already we have seen. In case of RC inductive, we have R here, C here, R is much greater than XC, then L equivalent. So it is inductive. So we have to find the equivalent inductance, that is RC upon GM. Again, RL is inductive. Here L and R is connected, but XL is much greater than R. Then it is again inductive, so that value is L upon GM into R. RL capacitives, here R and L is connection. Again, you are seeing that R is much greater than XL, then C equivalent is a GM into L by R. So for the different conditions, we have different formula here, and you can recognize the circuit, how it is going to be inductive and capacitive. So here we have taken our example for the capacitive one. Now another is the transistor reactance modulator by using the BJT. So either we are going to use the Hartley or Colpit oscillators. That is also here we have Clap-Goriot. Okay, Clap-Goriot oscillators are used mostly, but it is isolated with the buffer. Buffer is what your RF chokes that provide the DC path. Is going to allow the DC components. It's going to stop the AC components. So in this circuit, you can see that if you look that part from here, if you try to divide two parts, so this is the transistors, here also transistor, then you have this is the coil is connected to the source here, this is RFC, again RFC here, then RD, this is the voltage divider, here also we have voltage divider. Okay, now here input is given here, so this is given to through this resistance R, and here this blocking capacitor we have CB, and this is about already you know about bypass capacitor CB, which is connected between emitter and ground. This is the emitter resistance. So these are the similar connections, and here we have coupling capacitors, and finally at the output what we are seeing, we have like a Garriott oscillators C1, C2, and this is the variable capacitor, and we have inductors from where we are going to get the modulated FM as the output. So here message signal is given as the input. So and this is the first stage is going to act as the reactant modulators. Okay, and here this is the oscillator parts. By the help of this circuit, you can see how oscillation is being produced, and we are able to get the modulated output here. Third one is by using the Varactor Diode Modulators. So this Varactor Diode is the voltage variable capacitors. Okay, so this just junction capacitance is going to change with the help of applied voltage, and when diode is going to work in the reverse bias. So it's going to provide the automatic frequency correction for the FM transmitters and for the remote tuning. So it having two terminal device, so it has some limitation. So finally, this is the circuit diagram of by using the Varactor diode. So this connection is coming from the tank circuits. Here we have capacitors. This is the Varactor diode. Then we have this is the coil. Again, capacitor is here. Finally, we have this is like a transformer like arrangement, and here input signal is given. So like this, how this is being utilized to produce the FM signal. Okay, so here you see that AF input is given, so that tank circuit diagram is not drawn here. Our output we are getting from where? From the tank circuit. Okay, so this is how we are able to generate the FM by using the direct methods and the indirect methods. So direct method, we have seen that reactance or that is it can be capacitive, it can be inductives. So we have seen by the help of FET, BJT as well as Varactor diode, and indirect method we have seen by using the Armstrong methods. So if any doubt is there, you can write in the comment box. Thank you. Thank you very much.